Okay, so in this video, we're going to go over an introduction to confidence intervals. And we're going to look at it from the perspective of a confidence interval for proportions. So this is more of an intro. Okay, so what are just confidence intervals in general? So confidence intervals are used to estimate unknown population parameters. As I said, in this particular video, we're going to be looking at the proportion. But there also will be confidence intervals for means, and we'll tackle that concept in a different video. So confidence intervals are basically a way of estimating an unknown population value, an unknown population proportion. Confidence intervals they're calculated from samples. So what you do is you collect a sample and then you go through a formula and you're able to create an interval. A sample proportion is calculated. And then something called a margin of error is added and subtracted to that sample value. Okay, so if you've ever, especially we're coming up close onto election time, if you ever listen to election results and they say, oh, so-and-so got 30% of the vote plus or minus 3 points. That plus or minus 3 points, that is the margin of error. That's telling you that, listen, they got anywhere, we're estimating that they got anywhere between 27 and 33% of the vote. How did I get those values? I took the 30% and I subtracted and added that margin of error. Okay, so how do we calculate the margin of error? Well, here is the formula for the margin of error. Okay, and we use ME to represent margin of error. So margin of error is, we have a new symbol here, Z star. We'll explain that in a second. That's called the critical Z-score. So you take that critical Z-score, Z star, and you multiply it by the square root of P hat times 1 minus P hat over N. Okay, so hopefully some of these symbols are familiar to you. I know the Z star may not be, but P hat, we know that is a sample proportion. P hat is a sample proportion. N is your sample size. And as I said earlier, Z star is what we refer to as your critical Z-score. And I'll show you how to calculate that in just a second. So once we have our margin of error calculated, then as I said before, the confidence interval is found by taking your sample value, in this case the sample proportion, and then both adding and subtracting your margin of error. And what you're seeing me do here in this last one is I'm just filling in that formula for the margin of error that we calculate in the step above. Okay, so right now out of this formula, let's focus on that Z star, that critical Z-score. That is the most important value that we should focus on right now because it's the one that we haven't talked about. So critical Z-scores are based on your confidence level. So whenever you do a confidence interval, you should always specify what level of confidence this interval represents. Okay, so let me show you how to do that. So for example, let us find the critical Z-scores for both a 90% and a 95% confidence interval. Okay, so how do we find these critical Z-scores? Well, this is what you do. As we always suggest in stats, if you can, if possible, draw a picture. So we're talking about Z-score, so we're talking about a standard normal distribution. So let's draw that with our familiar bell curve. And we are talking about Z-scores here. So these are values of Z-scores. We know that the standard normal distribution, the Z distribution, has a mean of 0. So right now in the middle is where Z is equal to 0. We know the standard deviation is equal to 1. So let's focus on, let's do the 90% confidence interval first. How do we find the critical Z-score? Well, this is what the picture looks like. Okay, what we're going to have is we're going to have a critical Z-score both to the left and to the right of our center. They're going to be equal distance apart, and because of symmetry, the only difference between them is that the left one is going to be a negative because it's to the left of Z equals 0, and the right one's going to be a positive. Okay, but whenever we report the Z-score, the critical Z-score, Z star is always positive. Always positive. Okay? So, where does the confidence level come into play? We are 90% confident. What that means is that in between those two unknown critical Z-scores, the shaded area between them is the confidence level. So all this that I'm shading in between here, this is 90% because we need to be 90% confident. Okay? So now what we need to figure out is what z-scores kind of fill out this situation. And to me, folks, the easiest way of thinking about this is this. Okay? So remember, we know with the normal distribution, we have a total of 100% area underneath the curve, or 1. Well, if 0.9 or 90% of my area is shaded, what percent is not shaded? That's 10%, right? 0.10. And because of symmetry, we're going to take half of that unshaded area and we're going to put it in the right tail, and we're going to put the other half in the left tail. So what I'm saying is this right unshaded tail area should be 10%, my remaining unshaded area, divided by 2, which gives me a 0.05. Okay? And for the exact same reason, it's a 0.05 in my left side there. Okay? So once again, we're talking about areas. So it should be clear, hopefully, that both of these 0.05 should be positive, right? Because I can't have a negative area. That makes no sense. My z-score could be negative, but area itself is always going to be a positive value. All right, so the way I'm going to tackle this is I'm going to find, I think it's a little easier for us to find the negative z-score, and then we know that the positive version is going to be our answer. Okay, so how do we find that? Well, we need to find the z-score that has area to the left of whatever's in your left tail. And in this case, it is 0.05. So what we're going to do is we got to do a reverse lookup. So I'm going to pull up some z-tables here. And we are going to find the area inside the table of get as close as we can to 0.05. And then we're going to back out what that z-score is. And that'll be our answer. Okay. So here's the z-tables. And so remember, we're trying to get as close as we can to a 4-digit area of 0.0500. So as we look around here, it may take a little minute here, but we should. Here we go. Looks like we're getting close around here. We have a 0.0505, and we have a 0.04947. Okay? So those both seem to be pretty close to 0.05. So, I mean, technically speaking, which one's closer? I believe this, the 0.050 is a little closer, right? So that means that our z-score will be, let's back that out, that's a negative 1.64. And then also the other one that we're really close to is a negative 1.65. So really what most people will do in that case, because those two values are so close to each other, what most people do is they'll split the difference. And they'll say that this z-score is a negative 1.64 and then 5. That third digit of 5 means I'm going halfway in between negative 1.64 and negative 1.65. Okay? At least for a homework system, you'll be fine if you just use a negative 1.65 or a negative 1.64. But I just wanted to show you why most people use a negative 1.645. So that means by symmetry, our critical z-score is the positive 1.645. So there we go. So for a 90% confidence interval, if we want to calculate the margin of error, we should use a critical z-score of a 1.645. All right. Now let's quickly do the same thing for a 95% confidence interval. Really, it's a very similar picture. The only thing that changes is the area in between. All right, so right down the middle, z is equal to 0. We have a left critical value, and we have a right critical value. But now the area between them for a 95% confidence interval is 0.95. Okay? So now that means what's the area, right? The unshaded area here in these tails. Well, if I have 0.95 that's shaded, that means I have 0.05 that is left over. Take it and divide it. Ooh, that should be 0.05. Always take it and divide it by 2. So you take your unshaded area and divide it by 2. That gives us a 0.025. I want to make sure this is extra clear. This should be a 0.05. If For that exact same reason, we have a 0.025 in the right tail. So now we're going to do the same thing. We do a reverse lookup in our z-table. We get as close as we can to a 0.025, and that will give us a z-score. So it's going to be a negative value. So let's see here, a 0.025. Let's see. Oh, we land on it really close right there. So hopefully you guys can see this on video. So what is that z-score? Backing it out, it's a negative 1.96. So the z-score, the negative z-score, I'm sorry, that should be a negative there, is a negative 1.96, which means our actual critical value that we're going to use is a positive 1.96, right? And that makes sense, right? Because remember we said with the 68, 95, 99.7 rule, we said that about 95% of the data is within 2 standard deviations of the mean, right? That's what that z-score is. That's really, really close to 2. So it's nice when that matches up. But anyways, that's how you get the z-score there, all right? So just if you want to write this down in your notes, the common values for a z-score are as follows. So for a 90% confidence interval, as we see, we use a 1.645. For a 95% confidence interval, we use a z-star of 1.96. Okay, and so there are other, confidence interval or confidence levels we could use, but hopefully now you understand that process of how we get those z-scores. Okay, so I just wanted to show you really quickly a really quick way of actually finding our critical z-scores without using a table. I just found this out, so this is why this is kind of coming in at a weird time in the video. But all we have to do is go to our normal stat calculator. So we go to stat, we go to calculators. Let me grab my mouse here. Go to calculators, then we go to the normal calculator. And let's say we wanted to find the critical z-score for the 90% confidence interval. So what we're going to do, let me zoom in a bit here, is since it's a z-score, the mean is 0, the standard deviation is 1, okay? But what we don't know is the actual z-score, right? But what we do know, if we come over here, I'm gonna scratch this out, what we do know is the area we want to the left, okay? Or in fact, if we want to, we could do the area to the right. But anyways, we know the area to the left. So for 90% confidence interval, remember there's 10% that's left over, and we divide that by 2. So that's where I get a 0.05 from. Okay? If I go ahead and click compute, boom, it automatically populates. Hopefully you guys can see that. It automatically populates our z-score being a negative 1.645 if we go to 3 decimal places. Remember the critical value should always be positive. So that's why the critical z-score for a 90% confidence interval is a 1.645. Well, how about this? What if I wanted instead the area to, I wanted the critical z-score for the 95% confidence interval? Do the same thing. In fact, I'm going to do it this way. Can I do a 0.05 divided by 2? Okay, let's do it that way. Because what this means is that I have a 95% confidence interval. That means 0.05 is not shaded. And remember, we take half of that. So if we compute that, that doesn't quite work. Okay, so let's do it this way. 0.05 divided by 2 is a 0.025. Hit compute, and there we go. We get a z-score of a negative 1.96, which if we take the positive version, we get a positive 1.96. Okay, so I just wanted to take a quick second and show you guys how we can easily get the critical z-score using our StatCrunch calculator. So there's no need for us to use the table. So now we know that we have these different critical z-scores. Notice that as our confidence increases, our z-score gets a little larger. Well, what is that going to do in terms of the margin of error? Well, remember the margin of error is based on that z-score. So the larger our confidence level, the larger our margin of error. which means that we will have a wider confidence interval. Very important note right here. So the more confident we need to become, the larger our interval will be. All right. Imagine like this. I use the analogy of, imagine if we're on a boat and we're asked to capture 90% of the fish in the ocean. So we cast a net, right? But now our boss calls us and says, now you need to catch 95% of the fish in the ocean. Now we have to cast a wider net. So that's why as your confidence level increases, so does your confidence interval as far as the width of it, okay? All right, and then moving along here, what in the world do we mean by 95% confidence? This is where I want to take a few minutes and discuss really quickly, okay? So consider an example where we are interested in knowing the proportion of all college students that have a GPA of at least 3.0. Okay, so we want to know the population proportion or the population percentage of all students, all college students that have a GPA of at least 3.0. Right? And so this is, hopefully you can see why this is where confidence intervals come into play, because it will be very, very difficult for us to calculate that population value. That means we'd have to get the information of every single college student. That's not practical. Anyways, suppose we take a sample of college students and we get a 95% confidence interval that goes from 0.55 to 0.65. What does this mean? Okay. All right. So let me start off with the most common incorrect interpretation of what this confidence interval is saying. So when some people see that 0.55 to 0.65 and they see it's a 95% confidence interval, they will erroneously say, oh, there is a 95% chance that the population proportion, which we don't know, is between a 0.55 and a 0.65. That is incorrect. Okay? Incorrect. Okay? That's not what a confidence interval is measuring. And I'll tell you what it is in just a second, okay? The reason why this is incorrect, because either the population proportion is in between that interval or it's not. So that is an incorrect interpretation. All right. Or some people will say we are 95% confident that the sample proportion is between 0.55 and 0.65. That is also correct. And the reason why this is incorrect, because this is very close to the correct interpretation. It's incorrect because it's talking about the sample proportion. We know what the sample proportion is because we calculated a sample, and that's how we were able to calculate the 0.55 to 0.65. Okay, that's how we're able to calculate this. So we know the sample proportion. A confidence interval talks about a population value. So it's very, very important. So what is the correct interpretation? It is this. We say that we are 95% confident that the population proportion of all college students with at least a 3.0 is between 55% and 65%, or 0.55 and 0.65, either one. So the key here is that we are saying that we are 95% confident. We're not saying there's a 95% chance or any of that. We're just saying we are 95% confident. So what in the world does 95% confidence means? Well, hopefully this will make it clear here. 95% confidence means that if we repeated this process a bunch of times, okay, what I mean by that is that we get a sample of students and we calculate the sample proportion from that sample. If we repeated this process a bunch of times, first of all, what's going to happen is that every time we get a different sample, we're going to get a different confidence interval. It's very important to understand. Every time we get a different sample, we're going to get a different confidence interval. But what the 95% confidence means is that if we did that a bunch, we got all these different confidence intervals, we would find that approximately 95% of all of those confidence intervals generated from different samples would actually contain that true population proportion. So the 95% confidence is a statement on how strongly we believe in the process that we did. Okay? So once again, but the key I need y'all to understand is that every time we take a different sample, we're going to get a different confidence interval. And I believe I say that here. Remember, each confidence interval is generated by a sample. So different samples will generate different confidence intervals. Very, very important. Okay, so the last bit I want to touch on here are the necessary conditions to calculate a confidence interval. We'll do these actual calculations in another video. So notice something familiar in the formula for the confidence interval. Let me go back and tell you what's looking a little familiar here. Let's see here. Yeah, let's go back here. You guys see this thing right here? This square root of p hat times 1 minus p hat over n? That looks familiar. It should look familiar because that came from the central limit theorem for proportions, right? And so that's what I want to make note here. Notice something familiar in the formula for the confidence interval. Yes, the standard deviation of a sampling distribution, aka from the central limit theorem. But however, since the central limit theorem standard deviation, we use p's in the formula. It was p times 1 minus p over n, square root of that. Well, since we're using sample proportion, the p hat, we call it the standard error. So I just want to give you a little bit of terminology here. Because we're not using p and we're using p hat, we call it the standard error. But anyway, since the confidence interval is based on samples, hence sampling distributions, the conditions necessary will be the exact same conditions that we talked about when we did central limit theorem for proportions. Okay? What were those conditions? Remember, we need an independence assumption. We need independent data values. And how can we check for that? Either we can make that assumption based off the scenario, or we can say, hey, if you did random sampling, we can safely assume that we have some independence there. Also, we check the 10% condition. Remember, we need to make sure that we sample less than 10% of the population. If we sample too much, we're going to end up with a dependent situation. We don't want that. We want to keep independence. And then lastly, we need a large enough sample size. So if you recall the central limit theorem for proportions, to get a large enough sample size, we checked n times p. Well, this time we're going to check n times p hat, n times the sample proportion. We need that to be greater than or equal to 10, and we also need n times 1 minus p hat to be greater than or equal to 10. Remember, we refer to this as the success and failures condition. We need the number of successes and the number of failures to be greater than or equal to 10. All right, if those conditions are met, then you can go ahead and calculate the confidence interval by using this formula we talked about earlier. You take your sample proportion and you add and subtract your margin of error, where the margin of error is the critical z-score times the square root of your p hat times 1 minus p hat over n. In fact, we call this confidence interval a one proportion z interval. Okay, one because we're taking one sample at a time, proportion because we're dealing with proportions, and z interval because we're dealing with the z distribution. Okay, so as I said, in the next video, we're going to go through how do we actually calculate a confidence interval and interpret it correctly. I'll see you guys in the next video.